As you start working through the 3.1 homework, you're going to notice that there's a lot to do with graphs and connecting ideas between graphs and different points and different ideas in the function, a lot of which we talked about in class. This is just sort of a deeper dive. So if you haven't read questions 1 through 7, maybe just go peek at them before you start watching the video. In all of the questions that talk about a vertical intercept, they're really trying to tell you where the function crosses the vertical axis. Crosses the vertical axis. Get that in here. So in pink right now on my axes, I'm going to identify my vertical axes as those that run up and down. Right, this one axis runs up and down. And wherever my function, let's put it in a different color. Say I have a function that looks like this. Some sort of linear function in this case because my graph is a straight line, so I know it's a linear function. I can identify immediately what the vertical intercept is by figuring out where it crosses the vertical axis. The horizontal intercept is where the function crosses the horizontal axis. So in blue on my axes, I'm going to identify that point on my horizontal axis, which is my left to right axis. This is typically my independent variable axis, and I'm just going to mark this point here. What's important to remember is that the coordinate of my horizontal intercept, it has a very particular form. The horizontal intercept, it's where we're crossing the horizontal axis, and the axis itself is where the height of the function is 0. The height of the function is 0. So with this point, you can notice that since the height of the function is 0, this point has the form if let's say this is some sort of xy coordinate. It doesn't always have to be x and y, but in this case we'll say x and y, and I'll label accordingly on our graph, x and y. Then the y coordinate is 0. That's where the height is equal to 0. Let's go back up to the pink here. We have the vertical intercept. That's where the vertical axis is crossed. Looks like I left off a couple words here. And the point of a vertical axis has the form. It's similar to a horizontal intercept, except in this case, the x is 0. And the way that this works is if this is our xy, the x is 0. And let's go back to our graph and look at that point. So I'm trying to make it just a little bit bigger. What you can see here is that we have not gone left or right from the axis at all. We've gone 0 units left and right, which is why our coordinate has a 0 in the x location. So I redrew a new linear function on our coordinate axis because we need to talk about another important concept, which is slope. With a linear function, the whole idea, what creates a linear function, is that the slope is a constant amount. So every single time I take a certain number of steps to the left along my function, or to the right, I go up or down a certain number of steps, and it's the same every single time. So if we wanted to look at our example graph over here to identify the slope of this graph, we can use a formula. Slope, sometimes identified by the letter m. M is equal to rise over run. That's the whole idea of it's the amount that we go right to left and the amount that we go up and down. So all we have to do is really count from known point to known point on the graph, and it'll give us the slope. So let's look at our linear function on the graph. I see that we've got an intercept on the horizontal intercept. I've got a vertical intercept. And then I went ahead and put 2 more points and just identified those as known points on the graph. And what we can do is start at any one of these points and work our way to another point and just count how much up or down we go and how much right or left we go. So it's pretty convenient to start at the intercepts. It doesn't matter which one you start at. You can use both intercepts, to be honest. It won't make a difference. I'm going to start at our horizontal intercept, and I'm going to work my way up the function until I get to our y-intercept. So what we have to determine is how far left to right do I have to go to get to the y-axis. I have to go 1 unit, 2 units, 3 units. That's 3 units to the right. Going to the right is a positive direction for x, or for the horizontal variable. Now, if I want to continue my path, so I've made it from my point all the way over to the y-axis now, the vertical axis, I can now count upwards. How many units up do I have to go to get to this second point? I go up 1, I go up 2. I go up, so plus 2 units up. So let's take this to our formula. Our slope is equal to rise over run. We ran plus 3 units to the right, and we rose 2 units up. So this line has a slope of 2/3. Now where that fits into a linear function formula, we can look at the formula of the function like this. Y equals mx plus b. That's going to give us this function here, where m is the slope and b is the y-intercept. Okay, where b is the y-intercept. All you do is plug in those values or substitute in for m and b, and you wind up with an equation of this function. So for the function that's been graphed in front of us, we could get the formula. Y equals 2/3 x plus b. Well, what's b? We need to go figure out what is the vertical intercept. It's the point where we cross the vertical axis, and we can zero in on it here. We are plus 2 units up. We're up from the x-axis. So b is 2. And you now have the formula for this line, which you could put into your calculator and verify the format of it, and you could find any points on the graph from there using a table. I went ahead and drew a few fresh scenarios for us to consider, just as we're settling into this whole idea of slope. So I've got 4 lines drawn out here on our screen. 2 of these lines have a positive slope and 2 of them have a negative slope. 2 of these lines rest with a vertical intercept above the x-axis, so a positive b value, and 2 of these rest beneath their vertical intercepts rest beneath the x-axis. So we can identify these lines in this way. Since we're going in the first one, I'll go ahead and just label these so we have a way to talk about them. In the first graph, we have a function who's going up as we go right. This is a positive slope. Okay, so m is positive. And then our y-intercept is above the x-axis, so we have a positive b value as well. I'm just going to label this as b on the y-intercept over here for our formula. In graph number 2, we actually end up with a negative slope because we're going down as we go to the right. Okay, so anytime you see a graph that's tilted like this, we're going down as we go right, so we actually have a negative slope, but we still have that positive vertical intercept, so we still have a positive b value. In graph 3, we again have a positive slope because we are going up as we go to the right. This is rise over run I'm still referring to. But our b value is now negative because our linear function crosses the y-axis beneath the x-axis, and you can see that point's been highlighted there. Just like in graph 2, we are going down as we go right, therefore our slope is negative. This time our function crosses the y-axis at a negative value, just like in graph 3. So it has a negative b value, and of course all of these values that I'm referring to, m and b, that's still coming from the same formula as before, that slope-intercept form, y equals mx plus b. Slope, and this is your y-intercept. You should be able to use this information to solve problems 1 through 7 and then a few others at the end. If you haven't already, go ahead and pause the video and get set up for question 8. Make sure you understand exactly what's going on in the graphic as well as what's going on in the problem before you get started listening to the solution. I wanted to help with this problem because it starts off in kind of a tricky way, and it asks you to recall a certain principle about similarity between triangles. There's a small triangle here, which has 6 feet and 10 feet as its legs. And then there's a larger triangle, which goes all the way to the top of the tree and all the way to the base of the tree. From a geometrical perspective, these two triangles have the same side ratios. So in the small triangle, we should have, let's see, 6 feet in the vertical direction for every 10 feet that we go to the right. That should be the same ratio as however high the tree goes. However, the whole base is 30 feet. So we need to determine, using this proportion, there is another way to solve it, which I'll show in just a minute, but this is probably the fastest way to solve it. We use a proportion where we cross multiply. So we're going to do 6 times 30 equals x times 10. 6 times 30 equals x times 10. And 6 times 30, that's 180. Right, we're just solving this linear equation, trying to get x by itself. Since x is being multiplied by 10, we need to do the opposite operation to get it separated from that 10. So x equals 18. Okay. So the height of the tree, this is the leg that we were looking for. The height of the tree is 18 feet tall. The other way to look at this problem is a slope problem. If you were to just isolate this rope, just the rope, it looks like a straight line. There's tension in the line which causes it to be straight. So we can actually model it using a linear function. Linear functions are known to have a constant slope. So the rope from the ground to the light pole top has the same slope as the light pole up to the top of the tree, and from the ground to the top of the tree. The slope of this rope, the slope of this line, is equal to rise over run. Now there's a little hint about that already given in the drawing. It says I can run 10 feet to the right, but then I have to go up 6 feet in the y direction, up-down direction, the vertical. So if I need to go 20 more feet to the right, well, that's 2 sets of 10. So I need to go over 10 units to the right once and go up another 6 feet. 6 feet, I can label that. Then I need to go another 10 feet. This completes my 20-foot journey to the right, but I have to go up another 6 feet. It's this idea that the slope is constant. If I go over to the right 10 feet, I have to go up another 6 feet along this rope in the vertical direction. So we could simply now count up all of the units that we traveled up. In 3 steps, we've now traveled up 6 feet, then up 6 feet, then up 6 feet. That is, again, a total of 18 feet, this time using We're not using the geometry, we're using the algebra behind it. And I want to leave it to you to answer part B. I want you to really consider, if this tree, right here, if this tree starts falling, the rope is going to pull it in this direction towards the earth. Your job is to decide, where's the top of that tree going to land? Is it going to land before the light pole, causing no damage? Will it hit the light pole and cause damage, or will the tip be beyond the light pole, completely crushing it? So take some time and think about, will that tree hit the light pole? This problem has a lot of words going on. There's a lot to get you started and set up with understanding what's going on, so make sure you read that before you listen to the solution. However, if you've already listened, you can see that I've underlined probably the most easily mathematized sentence. Suppose that the highway is in fact a straight line. We know about straight lines. Those are linear functions with a slope of 0.28. Okay, so now I have some linear function. That's our general form that we're using, that slope-intercept form. But they tell us that the slope is equal to 0.28. Let's follow through with that. And that the elevation at the beginning is 6,000 feet. At the beginning. That is a height. An elevation is a height. They've just given us a starting y value, or a starting height, and we're going to use that to our advantage. That is one way to verbally give the y-intercept, which is your b value. Okay, so now you have the equation of the line of this highway that's going up the mountains. I went ahead and drew some random mountains, and I put a big dot here because I'm going to say that from here to here, I can model this stretch of highway using the line that we've just been given, because it's based off of the information that they gave us. So this line along this mountain, this is State Highway 108, follows the linear function y equals 0.28x plus 6,000. The question that they ask us is, if we are moving up the mountain, here we are, larger than life, if we're moving up the mountain, what would be the elevation after traveling 1.5 horizontal miles, or whatever number they've put in there? It's in red because it changes person to person. 1 mile is 5,280 feet. I'm going to travel, and excuse me for writing over what I've got here, I'm going to be traveling along the mountaintop, but the way that this has been described is that I'm going to go 1.5 miles horizontally. It doesn't say that I'm going to be walking along the road. It says, if I go 1.5 horizontal miles, how far up have I gone? I don't know yet. We need to look at our equation. My height is equal to 0.28 times whatever horizontal value I plug in, plus 6,000. Okay, this is going to take us to the final elevation. It's going to tell us how high we are when we finish. What would be our elevation after 1.5 horizontal miles? They're trying to be very tricky here. Your units so far have been in feet. Here they're trying to trick us with 1.5 miles. You have to convert 1.5 miles into feet. And the way that we do that is we set up an equation or some sort of expression that's going to convert, using a conversion factor, 1.5 miles into feet. So 1 mile is equal to 5,280 feet as given in the problem. Now you can see that I've got my miles on the bottom and my miles on the top. That's so that I can cancel those out. I wind up with only feet. That's what I'm looking for. So in your calculator, whatever value you have, I have 1.5 miles being transferred. or translate it into feet. So I take 1.5 and I multiply that by 5,280 in my calculator, and it tells me that in feet, 1.5 miles is equal to 7,920 feet. That's how far I'm traveling horizontally, and I'm going to go ahead and write that into my diagram to make sure I understand where these numbers are coming from. 7,920 feet. Now that number is my x value in feet, so I just have to substitute that into my equation for y. So y is equal to, and you can follow along with your calculator, 0.28 times 7,920 adds 6,000 is 8,000, let me get my pen back out, is 8,217.6 feet. I don't see any sort of restrictions on rounding or how many decimal places they want. So if it was me, I would go ahead and just put in that entire value. There is a little rounding tolerance built into the problem in the answer bank, but I would go ahead and just leave it with that one decimal place there. This problem and some of the other problems that surround it in the homework are all about slope. And they're trying to get you to consider the slope equation, the slope formula, from different perspectives. In a previous problem, you were given 2 points. They would have the form kind of like what I've written here, what's given in the problem. A1, B1, and A2, B2. That's like an XY value for one point and an XY value for another point. In this problem, it's something a little bit different. They tell us 1 point. I'm going to say that's my A1, B1. It could have been my A2, B2. I'm going to call it my A1, B1. I'm going to call that 5, 3. And they tell us the slope. So I don't have a second point here. What I have is the slope. The slope, or m value, is equal to 2. What they are asking us to consider is to find the point where the line crosses the vertical axis. Your job is to remember that where we cross the vertical axis, say we cross here, some sort of function like this going through here, the coordinates look like 0 in the x because we haven't gone left or right at all. We're right on the axis, and then some number in here for the y. At this stage, we do not know what that number is, but I know that my x-coordinate, my A2, is equal to 0 because that's the form of a vertical intercept. So let's go into our formula. Substitute known values. The slope is equal to 2. B2, that is our only unknown value. I'm going to leave that as B2. I subtract off B1 from that. B1 is 3. All of this is over A2 minus A1. A2 is 0. We know that value from the form of a vertical intercept. Subtract off A1. A1 is in the first position of our first coordinate pair, and it has a value of 5. So just simplifying a little bit, we have 2 is equal to B2 minus 3 over negative 5. In the past, I've seen people think that B with the little 2 means squared, but that would be if it was up top, something like this, which it is not. Okay, it's written below the B. Small and below the B is just a way to name B. This is B2, the second B. So let's continue this. I've got a fraction. I've got B2 minus 3 all over negative 5. I want to get rid of that fraction. I'm trying to work my way in towards B2. So I'm going to multiply both sides by negative 5 over 1. The way that this works out for our next step, I'm kind of working horizontally here. I've got negative 5 times 2 on the left-hand side. That gives negative 10. Is equal to my negative 5 in the top, my negative 5 in the bottom cancel out, so I just have B2 minus 3. We're trying to work in towards B2. I have a -3 associated with that. I need to do the opposite, which would be to add 3 to both sides. So if we look towards our next step, again, I'm working horizontally just for space on the slide here. -10 plus 3 is -7, and that equals B2. So my coordinates, x, y, let's bring it all together. I now have my B2 value that's going into this coordinate. So the final coordinate, the xy pair, my x is equal to 0. We could have known that from the beginning. You could have typed in 0 here from the beginning because we were dealing with a vertical intercept. Our job was to find that B2 value, that y value, which in this case was -7. So our point is 0, -7. Please do not try to type in the comma or any of the parentheses. They're already there for you.